All right, in this section, or in this video, we're going to cover section 6.5, the law of sines. And what this helps us do is to get away from having to deal with just right triangles. We can start to solve triangles or learn about triangles that aren't just right triangles. So I've drawn a standard triangle here, but not a right triangle. And we have angles A, B, and C, side lengths A, B, and C, and we always put those opposite of the angle. So capital A for the angle here, the opposite side is lowercase a. And then B and B are opposites, and C are opposites. Working out or writing down what the law of sines is based on this picture, we get that sine of A, sine of the angle A, divided by side length A is equal to sine of B over B. And that is also equal to sine of C over C, where it's that angle C. So this is our law of sines, that all of these ratios are equivalent to each other. And we can use that to determine parts of triangles. So our first example, and only example in fact, is going to be to use the law of sines to solve all possible triangles that satisfy the given conditions. A lot of times when we're given 3 parts to a triangle and we need to use the law of sines, we'll just get one triangle from that. We'll work through and determine the rest of the triangle, and it'll just be one triangle that will work for all of the information that we discover. But it turns out here, and we'll see in this case, that sometimes when we're using the law of sines, that if we're given 3 pieces of information about a triangle, in particular in this case, side length A is 24, side length C is 11, and angle C is 25 degrees, that sometimes we can have 2 different triangles with all 3 of these things occurring. So I've actually drawn a triangle here with side length 24, angle 25 degrees, so we have this line up here now, and then we have a line that is 11, right? And this C and C go together. So angle C is 25 degrees. Side C is 11. That is opposite, is the side opposite of that angle. So this side is 11. Well, there's a possibility here that really we have another triangle that is right here, where this is 24, angle 25 degrees here in between, and then side length 11. So I'm going to draw out both of those triangles. We don't know if this is the case yet, but it looks like maybe we have 2 possible triangles here. And then something like this. So I'll call this one triangle 1 and this one triangle 2. Again, maybe one of those triangles doesn't really exist. We'll actually determine that in just a few minutes. But it looks like it's possible that both of these could exist and satisfy the 3 given conditions that we have. So to start working on this, well, this was side length A, so angle A is here. This was side length C and angle C. So this is angle B and side length B. And this is, I'm going to say B sub 1, A sub 1, and B sub 1 for triangle 1. And over here, 24 is the side, so angle A is up here, this opposite, right, of our side. And then 11, side 11, and angle 25 degrees are opposites. And then we have B and lowercase b. And I'm going to name this B sub 2, A sub 2, and B sub 2 because it's triangle 2. Now, to start to work through and determine what these other 3 parts are, well, what do we know? We can use our law of sines up here. And our law of sines says that sine of A, so what we're going to try to do is determine what angle A is, over side length A, which is 24, is equal to sine of 25 degrees over 11. Okay, and this was sine of C over C. Well, we can work through this equation here to solve for sine of A. So this says that sine of A is equal to sine of 25 degrees times 24, all divided by 11. And if we work that out, this is equal to 0.922. So we know that sine of A is equal to 0.922. Again, you just plug that into a calculator. Make sure you use degrees since we were given degrees. And so sine of A is 0.922. So based on section 6.4, to find out what A is, we need to find arc sine of 0.922, or sine inverse of 0.922. If we plug this into the calculator, we're going to get approximately 67.2 degrees. Okay, so we have 67.2 degrees. Now, that's not the only solution to that, though. Right? Our calculator said 67.2 degrees, but there's another angle that when we plug in that angle, we get sine of that angle is equal to 0.922. So let's think through that. Well, first off, 67.2 degrees did that. But also, we're going to have another angle over here that has the same sine value. Okay, so that's the angle here. It goes from here to here. Well, what do we know? We know the reference angle. Maybe I shouldn't have used two lines, so just use one. That reference angle here is 67.2 degrees. So this angle here is 180 degrees minus 67.2 degrees, or in other words, 112.8 degrees. Okay. So then the question is, do both of these values work to produce two different triangles that satisfy these three conditions that we were given? So we need to test that. Well, first off, 67.2 degrees, absolutely that's going to work. 112.8 degrees, how do we determine if that works or not? Well, really, we just need to check to see if the interior angles will be okay. And how do we do that? Well, we know that the interior angles of a triangle have to add up to be 180 degrees. So 112.8 degrees, so this theoretical angle that we have on our triangle, plus the other angle we know about our triangle is 25 degrees. Well, is that less than 180 degrees? Absolutely it is, which tells us that our other angle B over here exists, right? If this added up to be more than 180 degrees, then B couldn't possibly exist. A third angle couldn't possibly exist since the three interior angles have to add to be 180. And if two of them are already greater than 180 or equal to 180, then we don't have a third angle. But in this case, when we do this addition, we get that it is less than 180 degrees, so that third angle can exist. So in fact, what this tells us is that we will have two different triangles, and that is angle A1, so the angle A for the first triangle is equal to 112.8 degrees. And angle A for the second triangle, though that was the 67.2 that we found. Then we need to find angle B. Well, angle B1, so that's this first triangle, well, that is equal to 180 minus this sum here, the 25 degrees plus the 112.8 degrees. This is 180 minus 137.8, which is 42.2 degrees. Okay. So we get 42.2 degrees, and that is our angle B1. And then we can do the same thing over here for angle B2. This is 180 degrees minus 67.2 plus 25. And that is 180 minus, let's see, 72.5, 92.5, or sorry, 92.2. And that is equal to 87.8 degrees. Okay. So we have all of the angles of both of our triangles now. So the final thing is to find out the side length B1 and B2. Well, B1, how do we find that? Well, we use our law of sines again. So this is sine of 42.2 degrees all over B1 is equal to sine of 25 degrees over 11. Well, if we solve for B1, this turns out to be that B1 is equal to 11 times sine of 42.2, again, we're all in degrees, divided by sine of 25. Plug all of that into the calculator to find B1. We do the same thing for B2 here, except we use triangle 2's information. And that is, of course, that sine of, and now we have angle B2, so that was 87.8. all divided by b sub 2 is equal to sine of 25 over 11. This tells us that b2 is equal to 11 times sine of 87.8 divided by sine of 25. And again, you plug that into the calculator and you can determine what b2 is. And that is it for this section. All of the problems in this section use the law of sines. This is the most difficult type of problem in that section, so I thought I would just cover that one. Yeah, that's it for this section.